Hi, my name is Trace, and today I'll be discussing inverse semigroups. So to do that, first I'm going to begin by talking about partial bijections. So if you've taken a group theory class, you know that Sn is the set of bijections on 1 through n. So like that. But what if we didn't want to consider full bijections? What if we just wanted to consider partial bijections? So let me give an example. So pi is 1, 2, 3, 4, maps to 2, 1, 4 dash. So these are things with set theoretic inverses. So here, pi inverse is going to be 1, 2, 3, 4 maps to 2, 1, dash 3. And I can actually compose these things with their inverses. So let me see what I get. Pi composed with pi inverse. So let's see, 1 maps to 2 maps to 1, 2 maps to 1 maps to 2, 3 maps to dash, and 4 maps to 3 maps to 4. So here I'll get a partial identity on 1, 2, 4. But notice it's not a global identity, because if I multiply this element by row, which is 1, 2, 3, 4, dash, dash, 3, dash, ultimately it's not going to be defined anywhere. So that'll give you an empty function and not like row back. So what's going on here? Well, these things behave a little differently than groups. And so let me dive a little into their theory. Okay, so it's a definition. Let x and y be sets. A partial bijection, which I'm just going to call PB, from x to y is an injective function from a subset of x, domain of x, to a subset of y, which we're going to call the image. So I'm going to describe the composition rule. So let's say I have G is a partial bijection from x to y, and let's see, y is a partial bijection from, or sorry, f is a partial bijection from y to z. Then G composed with F, or rather F composed with G, is a partial bijection from X to Z with its domain being G inverse of the domain of F intersected with the image of G. So this rule may seem a little complicated, but the idea is it's just elements which I'm allowed to take successfully first G, then F. Okay, so as an example, consider composing F, which is 1, 2, 3, 4, 5, 5, 1, dash, dash, 3, and G, which is 1, 2, 3, 4, 5, 5, dash, 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 3. And so I want to take G composed with F. Try this one yourselves. But if you notice, when I do F first, 1 goes to 5, which goes to 3. 2 goes to 1, which goes to 5. I can't define anything on 3 and 4. And then 5 goes to 3, which goes to dash. So this is the results of the composition. So now I'm going to give a few facts about partial bijections, and I'm just going to prove one direction, or one part of one direction. Top 1, x, y, z are sets. F from x to y is a partial bijection. Then I have F inverse F is the identity on the domain. F inverse is the identity on the range. For a partial bijection, G going backwards, back from y to x, then F equals FGF and G equals GFG holds if and only if G is F inverse. See, F inverse is F, and the 1A, 1B is basically the partial identity on the intersection, which is the partial identity of B times partial identity on A. The idea is partial identities multiply to a partial identity and they commute. And finally, E, G, F inverse is F inverse G inverse for partial bijection G going Y to Z. Okay, so I'm just going to prove part B going in this forwards direction, because in the backwards direction, if G is F inverse, I have F inverse F is just going to be F, and then F inverse F inverse is just going to be F inverse. So maybe the more interesting direction is to go backwards, or I mean forwards. So let's write proof of B forwards, and the others kind of follow from set theory. Okay, so B in the forwards direction. So let's see, suppose Yx is in G. So suppose Y is equal to Gx. So we know G is GFG, so we have GF, G applied to X. And since G is a partial bijection, we have X equals FG of X, which we know G of X is, oh wait, let me see. No, sorry. No, I did the wrong order, whoops. No, we have, sorry, X is G of Y, and G of Y is G F G Y. But since G is a partial bijection, since G of Y is G of Fg of Y, I have Y is Fg of Y. And so this is going to be F of X. And so I can invert F to get F inverse of Y equals X. And so Yx is an F inverse. So this implies that G is an F inverse. And the proof for F is in G inverse follows similarly. And this second piece actually gives us that F inverse is in G, because I can just switch the order in the relation. And from these two, we obtain that G is equal to F inverse, which proves the forwards direction. So I'm not going to prove the other ones. And okay, so let's move on to the final definition that we should know. So if we just restrict ourselves to partial bijections on just a set X, we're going to get the symmetric inverse monoid. So let me define that. Ix, the symmetric inverse monoid, of X, symmetric inverse monoid is the set of partial bijections on X. So this thing has a bona fide identity, just one on the entire set, and it has unique inverses. In the sense that for each F, there uniquely exists G, so that FGF equals F and GFG equals G. So hopefully we can see that from part B over here. Okay, so now we're going to move on to general inverse semigroups. Okay, so let's move on to general inverse semigroups. Let me erase this. Okay, so inverse semigroups. So let's first begin by defining a semigroup. So a semigroup S with an operation is a set S with, let's see, it's a closed binary associative operation dot. It is an inverse semigroup if for each S there exists unique S star, so that SS star S equals S, and S star S S star equals S star. So hopefully we can notice similarities between this and this condition. Okay, so inverse semigroups don't have necessarily a global identity, but they do have idempotency. So an idempotent E and S satisfies E squared is equal to E. Let me give a fact. A fact is that I of X, the symmetric inverse monoid, is an inverse semigroup. With idempotency to be these partial identities, basically partial like identities on just subsets of X. So let's prove a proposition about idempotency. So if E, okay, I forgot to say, let E of S be the set of idempotencies. Okay, so let's prove a proposition. Let's see, if E is an idempotent, then E star is equal to E. E of S, the set of idempotencies, is given by the set of S star S, or the set of SS star. Okay. S star star is equal to S. And then finally, ST inverse is equal to T inverse S inverse. Okay, so let's go to proof. So first, note that E will satisfy E times E times E is equal to E, and E times E times E is equal to E, which looks a little silly. But the point is that by uniqueness of inverses, this means that E star is equal to E. All right, the second part. So let's go in the this direction first. So let's suppose E is some idempotent. Then E is equal to E squared, which is E star E, which is E star. So E has a representation in either of these sets. So now going back, I just have to show that S star S is an idempotent, so S star S squared is S star S, S star S. So now I can combine the last three, so I get S star S. Similarly, SS star squared equals SS star, SS star. So let's combine the first three, so I get SS star. And so these two facts tells me these two things are indeed idempotencies. And we'll see later, but we actually call this one the domain idempotent of S. And this one the range idempotent of S. And hopefully we can see why based on proposition 1 part A, where F inverse F is the domain identity on the domain, and F inverse is the identity on the image. Okay, great. So, but unfortunately, okay, no, sorry. Let's do part C. So part C, S satisfies S star S S star is S star, and S star S is equal to S. And so this is by uniqueness of inverses, S star star has to be S. Okay. So what I was getting to is part D we actually can't do yet until we have a fact about idempotency of an inverse semigroup. So let me erase this. Actually, before I get to this fact, let me make a remark. Let's see. If I have the element, let's see, 1, 2, 3, 4 maps to 2, 3 dash dash. We can compute F star is just a set theoretic inverse. So let's see, 1 goes to 2, so 2 goes to 1, and 3 goes back to 2. So we compute that F star F is let's see. Should be, let's see, F1 goes to 2, 2 goes to 1, so 1, 1. 2 goes to 3, and 3 goes back to 2, so 2, 2. So F star F is this partial identity, and F star is, let's see, 2 goes to, it should be dash 2, 3. So if you notice, we call this the domain idempotent because it's the identity on the domain 1, 2. And then we call the second one the range idempotent because what's there? call this one the range idempotent because it's the identity of the range 2, 3. Okay, so now let's get to the big proposition regarding idempotents. So idempotents are enclosed under multiplication, and they commute. Okay, so let's prove this. So let E and F be two idempotents, and let X be the inverse of EF. Okay, so let's see here. So now we consider FXE. So note that FXE is actually idempotent because FXE squared is equal to FXE. Now just look at the middle. Now because X is the inverse of EF, we have, this is FXE. So FXE is actually not idempotent. Okay. So now we're actually going to show that FXE is also the inverse of EF. How do we do this? So FXE is also the inverse of EF. So the idea is FXE, EF, FXE. So merge these E's and these F's, so I get FXE, which is FXE squared, which is FXE. Okay, great. In the other direction, which I have to do, I have EF, FXE, EF equals, let's see, EF, X, EF, which I know X is the inverse of EF, so this will have to be EF. Okay, great. So now FXE is the inverse of EF, which we know is X. But we also know FXE is an idempotent. So EF star is an idempotent. And so EF star, which is EF, is an idempotent. Okay, so that proves one thing. So by similar reasoning, FE is also an idempotent. So now to show that EF is equal to FE, I'm just going to show that EF and FE are inverses. So EF, FE, EF is going to be EF, EF, which is EF. And FE, EF, FE is going to be FE, FE, which is FE. So EF inverse is FE. But we know EF and FE are both idempotent, so EF star has to just be EF. So we're done. Okay, so this is kind of an important proposition. So this will actually help us prove part D of this. So I'm just going to quickly jot down the proof of part D. Okay. So for part D, so I'm going to show ST inverse as T inverse S inverse. So all I have to do by uniqueness of inverses is just to do ST, T inverse, S inverse, ST. So that's going to be ST inverse, S inverse, ST. So I'm going to commute these central idempotent. So I get S star, S, T star, T. And that's just going to be ST. In the other direction, T star, S star, times ST times T star, S star. That's going to be, let's see, T star, S, T star, S star. Once again, commute these idempotent. So then I'll get T star, T star, S star, S star. And that's just T star, S star. So by uniqueness of inverses, we just get that T star, S star has to be the inverse of ST. And we really needed this proposition to do that. So before I move on, let me discuss a couple more propositions. So I'm going to leave proposition 3 on the board. Okay. So let's see. So proposition 4. If E is an idempotent and S is an S, then S star ES is an idempotent. And another proposition says that if I have an idempotent on the left, I can just move it to the right. We'll move it like another idempotent to the right. So let's kind of phrase that. So if E is an idempotent and S is an S, there exists another idempotent so that ES equals SF. Okay, so let's prove this. So for part A, let's see, all I have to do is just square it. So S star ES squared equals S star ES, S star ES. So now I have three idempotents in the middle. I'm just going to move SS star to the beginning. S star, S star, E squared S is equal to S star ES. So S star ES is indeed an idempotent. Okay, part B. Let F just be S star ES, which we know from part A is an idempotent. Then you just get F is S star ES. Now you have two idempotents at the beginning, so now just commute them. So that will give you ES star S, which is ES. Okay, great. And the final problem I'm going to prove for this section is proposition 5. Groups are precisely the inverse semigroups with exactly one idempotent. So that gives us a connection. That gives us a connection into group theory, which hopefully we have done before. Okay, so as a proof, suppose you have a group G. So G squared is equal to G. Then G has to be the identity of the group. And we know the identity is idempotent, so this kind of proves this direction. Okay, now the other direction, let's say S is an inverse semigroup. With unique idempotent E. Okay, so by this part of this proposition, I know that E has to be equal to S star S, or SS star, for all S. Well, I also know that E times S is S star S, which, SS star S, which is S. And SE is S star S, which is S. So E is an actual identity, and you have inverses. So in the group theoretic sense, so this is a group, so S is a group. Okay, so that completes this part of inverse semigroups. Now we're going to move on to the natural partial order and Green's relations. Okay, so now let's move on to the natural partial order and Green's relations. So let's see. Define the relation less than or equal to on S if S is less than or equal to T, if and only if S is equal to TE for some idempotent E. Okay. So what's the idea? Well, the idea is, okay, let's once again go back to the symmetric inverse monoid on 4 elements. If S is 1, 2, 3, 4, 2, 3, 4 dash, S is some kind of signal, and if I tag on an idempotent, let's say I tag on dash 2, 3 dash, this is actually going to worsen the signal. I'm still going to get the same information, but it'll just be a subset. So let's kind of see that. SE is 1, 2, 3, 4, see 2 maps to 3, 3 maps to 4. Right, so it's the same information, but I lose this first bit of information, which is why SE is somehow less than or equal to S. Okay, so let's prove proposition. Let me get more space. So proposition 6, the following are equivalent. S is less than or equal to T, S is equal to FT for some idempotent in S. S star is less than or equal to T star. So taking inverses doesn't flip the sign. S equals S star T, and S equals T S star S. Okay, so let's prove this. So for A implies B, I know I have S equals TE for some idempotent E. And by proposition 4B, I can just move some other idempotent to the other side. So I know it's going to be, let's see, FT. I have to, okay, there's a similar proposition that says I can do it at the beginning. So you get this. Okay, now B implies C. Well, we know if S is equal to FT, I can take inverses to get S inverse is T inverse F. And so this will imply S inverse is less than or equal to T inverse. All right, so that's two parts done. C implies D. Okay, so I know S inverse is less than or equal to T inverse, so S inverse is going to be T inverse times some idempotent E. So I'm just going to take inverses, so I get S is equal to ET. So now what we're going to have to do is show that this thing works. So let's do that. S inverse T is going to be ET inverse T, which is ET T inverse ET. And we know we can commute these two idempotency. So let's do that. Or no, I want to commute these two idempotency. So I'll get E squared T star T, which is ET, which is, let's see, ET is S. Okay, so now, kind of the complicated one, we have to show D implies E. So this implies E. So the idea is we're just going to substitute S to be this form, and then we're hopefully going to see this come out. So let's do that. T S star S is equal to T S star T star S star T. So that's T star S star S star T. Okay, we see these three idempotencies. I'm going to move this idempotent to the end. So SS star squared T star T, which is SS star T. Well, we know SS star T is just S. It's just S. Okay, great. And then I have just one more step. I have to show that E implies A. So I have to show that if I have this, then S is less than or equal to T. Well, this is just some idempotent. So E is less than, S is less than or equal to T, just follows. Okay, so that proves proposition 6. So I have a couple more propositions relating to the partial order. Okay, let's see. Okay, proposition 7. So less or equal to is a partial order on S. So we still haven't shown this yet, but so we'll see it won't be too bad. Let's see. If E and F are idempotencies, EF equals FE equals E, if and only if E is less or equal to F. Part C, if S is less or equal to T, and U is less or equal to V, and SU is less or equal to TB. Part D, if S is less or equal to T, then you'll actually have S star S is less or equal to T star T, and SS star is less or equal to T star. All right, so let's prove these. Okay, so for reflexive, I have to show S is less or equal to S. So this is not too hard to do. S is S star S. So this implies S is less or equal to S because this is just some idempotent. So now let's show antisymmetric. So this is reflexive. Antisymmetric. So let's do that. So since we have S is less or equal to T and T is less or equal to S, we can use these two parts to get S is, let's see, S is S star T, and S is, okay, so back to the antisymmetric part. If S is less or equal to T, so S is T S star S, T is less than or equal to S, so T is S T star T. Okay, so this is what I should have had. Okay, so now I'm just going to substitute my value for T in here. So T we know is this, S T star T, S star S. We know these two are idempotent, so we're just going to commute them. So we're going to get S star S, T star T, which is S T star T, which is T. Okay, so S is equal to T. And finally, we have to show transitive. So transitive, so for transitive, let's see, so I have to show that, let's see, if s is less than or equal to t is less than or equal to u, I have to show that s is less than or equal to u. So here I'll have, let's see, s is equal to t, and t is equal to u times f for some idempotency e and f. E and f idempotency. So that's going to yield that s is equal to t u f. Is that right? Yes. Oh, sorry. No. S is equal to u f e, and f e is the idempotent because idempotents are closed under multiplication, and so this yields that s is less than or equal to u. Okay, so we showed it's a partial order. Next, I have to show that if e and f are idempotents, and e is less than or equal to f is if and only if this. So we know that e is less than or equal to f if and only if this condition, e equals e star f, which is ef, and we know idempotents can be, so this is equal to fe. So that one's not too bad. Okay, part C. If s is less than or equal to t and u is less than or equal to v, I know that, let's see, s is going to be te, and u is equal to vf. And I can put the f, let me see. I'll put the e at the beginning. So remember, we can choose to have the idempotents at the beginning or the end. So we have s is equal to et and u is equal to vf. So su is equal to et vf. So we know this is going to be less than or equal to etv because of this idempotent at the end. And then it's equal to less than or equal to tv because of this idempotent at the beginning. Okay. And then finally, part D is just going to be a consequence of this because if s is less than or equal to t, we know s star is going to be less than or equal to t star. And hence we can multiply these two things in either order. So we have s star s is less than or equal to t star t, and ss star is going to be less than or equal to t star. Okay. So finally, I want to prove one more thing about the natural partial order. Okay. So we're going to prove that if I just look at the set of idempotents, then this natural partial order on the idempotents is a meet semi-lattice. What does this mean? It means for any two idempotents, there exists a greatest lower bound. Okay, so let's do this. So for E and F, I already know that EF is a lower bound for E and F. And now let I be some idempotent which is less than both. If I multiply these two things, I get I squared is less than or equal to EF. And so EF is bigger than any other lower bound, so EF is the greatest lower bound. Okay, so now let's just give an example because that was just a lot of theory. So as an example, in the symmetric inverse monoid on 3 elements, let's look at the partial order on, let's look at the partial order on just its idempotents. So we're actually just going to get a, as we said above, a meet semi-lattice. So let's do that. So you have the partial identity on 1, 2, 3 is going to be above the partial identity on 1, 2, partial identity on 2, 3, the partial identity on 1, 3. And then these things on the second level are going to be above partial identity on 1, partial identity on 2, partial identity on 3. And so something like that. And then finally you have the empty function at the bottom. Okay, so that kind of wraps up the section on natural partial order. So now I'm just going to move on to Green's relations. So let me erase this. Okay, so for Green's relations, there's going to be 4 Green's relations. You have S is L related to T if and only if S star S is domain idempotent is T star T. S is R related to T if and only if SS star is TT star. S is H related if it's both L and R related. And then S is G related if only if there exists X. So that S is L related to X and X is R related to C. Okay, so these relations are actually important in like a general class of semigroups, but in inverse semigroup they take on this particular form. Okay, so the structure of Green's relations can be kind of identified in an egg box diagram. So this will be a diagram of a bunch of squares. And you're L related if you're in the same column. You're R related if you're in the same row. You're H related if you're in the same cell. And you're G related if you're in the same square. So I'm going to give, in a moment, I'm going to give an example and we can see all of this at play. Let me just first write down this fact because we're not going to see any interesting H classes in our example. So the H class of an idempotent E is a group with identity E. So the idea is to H, let's see, let me just give an example. So 1, 2, 1, 2 is actually going to be an H related to 1, 2, 2, 1 in the symmetric inverse monoid of two elements because they have the same domain and range. And it turns out that for an idempotent, the H class of just that idempotent is just a group. Okay, so now let me kind of end the presentation with a big example. Okay. So let's see. So consider the inverse semigroup in the symmetric inverse monoid on 11 elements generated by 7, 8, 9, 10. 7, 8, 9, 10. 1, 2, 3, 7, 8, 9. 4, 5, 6, 7, 8, 10. And 11, 7. Okay. So in a moment, I will write out all the D classes through the magic of editing. Okay, so now I'm back with all the D classes. We have the 0 D class, and we have 5 non-zero D classes. So if you notice, 2 elements in the same column are going to be L related, and they all have the same domain. And then 2 elements in the same row are going to have the same range, and they're R related. Maybe R for range. And then finally, notice that any 2 elements in the same D class have the same number of elements, but the converse is not necessarily true because these 2 are D classes with having elements of size 3, but they're not in the same D class. Okay, so now to see something interesting, let's just consider the natural partial order on just idempotents. So I'm going to color these idempotents different colors depending on which D class they come from, and we're not going to include 0, but you can imagine 0 is just at the bottom. So you have blue. Let's do purple for the doubles, and then green for the singletons. Okay, so at the top we have 7, 8, 9, 10. 7, 8, 9, 10. So this is going to be above 7, 8, 9, 7, 8, 9. And 7, 8, 9, 7, 8, 9 is in the same D class as 1, 2, 3, 1, 2, 3, which is over here. And this is going to be above 7, 8, 7, 8, which is the purple D class. 7, 8, 7, 8, 1, 2, 1, 2, 4, 5, 4, 5. And then this is going to be above the singleton D classes. So hopefully you can see 1, 1, 7, 7, 4, 4, 11, 11 is by itself. 7, 8, 10 is going to be in the orange D class. And then 4, 5, 6 is with it. And finally it connects like this. Does So if you notice, the partial, hopefully you can see it well. It's hard to see with the different colors, but the natural partial order on idempotenents kind of follows the same for two elements in the same D class. I have two elements in the red D class, and below them there's a purple D class and then a green D class. So the idea is this is kind of a general phenomenon that happens in semigroups. But thank you for listening to my presentation.